Hi, it's good to be here. I actually studied in these rooms like ages ago. I came here from Amazon in Gdańsk, where I work on Alexa speech technologies, ranging from speech recognition to text-to-speech and some language understanding in the middle. And I'm not a scientist, but sometimes I do science and weird things happen. We work on machine learning for all of the areas of artificial intelligence, voice recognition, speech synthesis, and we work with machine learning scientists. We work on applied scientists. We have a machine learning group that works on speech science in Gdańsk, another one, a couple of others in Europe, in Cambridge, UK. And a couple of groups across US, obviously. And today I will talk about some more practical aspects of machine learning that we are working on. And this relates to a feature of Amazon Alexa that we have just recently launched, which is the ability to talk to Alexa while the device is offline. And typically, that artificial intelligence assistants are beasts that only live in the cloud because they require massive computing powers that are only available there. And for a good reason, because there is also the functionality that the customers need is typically also in the cloud, so playing music and interfacing with some web services is also there. But there are some cases in which you could actually imagine that what you are trying to do is also, at least technically, available or achievable locally. And the things that we can now do is, it has a very elaborate name, which is called local voice control. And the newest Alexa devices can now talk to and handle your smart home, even if your internet connection is down. So typically that means that you will have to have a Philips or a Wemo or other kinds of Wi-Fi control device, and Alexa will, when she is offline, she will be able to still talk to those devices, recognize what you talk, and ideally, of course, our goal is so that the customer doesn't even know, or at least it works as it should offline. Now, before we got to launching this, we actually started with what at Amazon we call a working backwards approach. So it was like 2 years ago, so ages. And we've analyzed reasons to do this, to go into these offline scenarios, and identified a couple of use cases. So smart home is just one of those use cases. And what features do customers need? And apart from smart home, the other key area that we have identified is actually automotive. So when you are driving, you probably always not always are online. And especially in countries like Poland, where the coverage of the mobile networks is pretty poor, that's really true. And actually, when we were testing this later, it turned out that in the US it's also true. And so we had those two. Two broad areas, but in both of those areas we had restrictions. So the devices that we are working with are not especially powerful. We knew that they aren't especially powerful. On the other hand, we knew that what we are going to do with those devices is not going to be the same kind of Alexa experience that we have in the cloud. So you are not going to ask Alexa to play any arbitrary music that is out there in Spotify catalog, because Spotify is not available. You are not going to ask Alexa to open a skill which checks your recent posts on some website. But you might want to, when you are in the car, you might want to check how to get home, or you might want to play music that you have available locally on your either USB drive or your phone, actually. So on one hand, we had those limitations on feature side. On the other hand, we had limitations on hardware side. So we've seen some future here. So perhaps we were able to shrink what we are doing in the cloud to the environment, like Raspberry Pi sized environment of those devices, and do something. And still, we were thinking about setting goals and constraints in a way that was not restricting us, because we didn't yet know what kind of requirements we had on the hardware side. So we speculated what kinds of deployments customers would be able to accept or work with, or actually feel comfortable around. And how could this home device that you talk to or that enables you working locally look like? And we've actually thought about something like this. And there are people like me that have something like that at home, but I'm apparently not the typical customer. And while it's feasible for somebody to have a server rack at home, you probably wouldn't hold one in your car. This is an automated driving kind of experimental setup, and it's not as bad as early Google ones. So it's actually quite tidy in there. Still, what we wanted to achieve was something different. So we decided that this is not going to be feasible. We did some studies. We found out that customers are not going to likely to get this one for free, not even buy it, right? So what we want to do is pack it into this. So this is actually our current generation Echo Plus device. And internally, it's not a very powerful beast, but it has some resources that we can work with. And in the car, we want to make it integrated with whatever hardware we actually find there. Car hardware is, I'm not sure how many of you have ever worked with car hardware that's not autonomous driving, but it's pretty poor. So if a car maker can spare some money on something, they will do it, and it requires a lot of convincing to invest in CPU processing power, even if it's potentially valuable to a customer. So the first thing that we thought about is, well, we have this Alexa in the cloud, right? So this is on a broader level how the whole cloud Alexa ecosystem looks like. And devices connect to some endpoint, talk to an Alexa service. This Alexa service talks to some skills. The skills respond with actions, and actions get sent back to the device in form of typically speech, because actions happens separately from actually interfacing with the device. While this looks like a simple couple of blocks in this picture, underneath there are services. So each of those blocks is not just one service, it's hundreds of services. In some cases, we have hundreds of skills that we build and thousands of skills that people have built. So there is orchestration that powers all of that, and then there are services that build machine learning models for those other services. Or ingest data or process this data. So it gets pretty complicated. So how do we get there? So can we put this cloud into this box? And this crappy animation can do this, but practically it's a bit more complicated than that. So what we thought that we would do is look at the technology that we have and start from ground up. So how does the actual process of talking to Alexa or to any other voice assistant, for that matter, look like? So it's basically composed of 4, broadly speaking, technologies, which is ASR, speech recognition, NLU, language understanding, and TTS, which is text-to-speech. And you take user speech on the left-hand side, you transform it into what they said as text. You can look at either the 1best or n-best outputs. There are some machine learning models inside, and you get like set Simon's bedroom light to 50%. Now, speech recognition models typically output words as they are spoken rather than words as you would want to parse them into your skills. So what natural language understanding does is it classifies the input into intents. what the customer is trying to do, and it also segments the input into slots, which are useful bits of information that are embedded within the sentence. So the slots in this particular sentence are Simon's bedroom light, which we identify that this is the appliance name. Value type is %, so we extracted a slot which describes this value increment, and a setting value which is 50, and we transform it to its numeric form. So now it becomes a function invocation. So we just talk to the skill and say, okay, so you have to invoke turn on appliance intent, look up for this Simon's bedroom light. There is quite a bit complexity there in entity resolution. So what we talked about is named entity recognition. So what the model can do is tag this saying that, oh, this is a name of the appliance, but it doesn't actually know or doesn't always know that there is an appliance that is named like this. So any kind of model can make some errors, and at this point where we are talking to the skill will actually look it up in its database, do some matching, some fuzzy matching, figure out whether we are talking about any light that is in a room which is named Simon's bedroom, or any light that is named bedroom, or perhaps some other combination of that, and try to find some vague match against what the customer has said, because customers are typically using some very weird variances of what they actually named their devices, and which is pretty natural. So if we take all of that, this looks much more simple than what we were seeing in the architecture diagram for the whole Alexa, actually. So we have just 4 boxes instead of God knows how many. And we can focus on each of those to try to fit them within some known resource targets. And actually, the last bit was the easiest one for us, because that's Amazon Glance is actually founded around Ivona acquisition. Ivona was a speech technology company. They were doing speech synthesis a long time ago. And they got acquired by Amazon, but before they got acquired to Amazon, they actually made text-to-speech for all kinds of various systems. So they did very light, very tightly built speech systems that were able to run on anything, essentially. And if you have any kind of a Kindle device, including the ink devices, the speech synthesis that's on those devices, at least the newest ones, is actually Ivona. So it's able to fit in pretty cramped environments and sound quite good. So we had text-to-speech, which actually could work on the device. It wasn't quite the case for speech recognition and natural language understanding. So I'm going to focus on those two in this talk. So we are going to talk about ASR and NLU, and actually we will start with NLU. So the way that the cloud models work for NLU, we are using we're using pretty simple modeling for NLU, all things considered. We have some neural models that do some very complex things, but most of the processings are actually FST models and statistical models. Now, when we were starting with this project, we initially thought that, okay, so if we only know that the customer is only going to use a single domain, which is home automation, then we could potentially just enumerate all of the sentences that they are going to speak, pack it into an FST, and there we have a solution. So we actually did that. So our proof of concept was just using FSTs. And it was using FSTs built with patterns and grammars and some machine learning magic to augment this data. And this was quite performant, but as we were going to closer and closer to testing this with more and more people, it turned out that while FSTs are good, they are not really that good. So the long tail became longer and longer, and we actually did a lot of improvements on top of FSTs to make them work in an embedded world, and did some automated FST generation. So we essentially were able to analyze the utterances as they are being used by the customers, build machine learning models from that. We don't actually look at those data because it's private, but the training code can look at this data. And it generated something that was useful. So we packed that into FST. And the more we packed into those FSTs, the more we realized that FSTs are not that scalable. So weighted FSTs get pretty slow when you have to compose large model, large grammar model with large personalization model, and then all the things become slower and slower. And while we were doing those things, we also had a research project going on, and I'm going to talk about that. So, statistical model. So initially, as a little background maybe, so we are using mostly maximum entropy models for intent classification, and we're using conditional random fields for sequence tagging, name entity resolution, right? Why those? They are pretty useful. They perform very well. They are not very resource hungry, and it matters in the cloud just as it matters on the device. However, not very resource hungry is a relative term. So those models are still pretty large. We are using tools like Mallet. Mallet is a Java-based, very popular natural language processing framework that builds those kinds of models and is able to run them very easily. However, the resulting models were acceptable in the cloud, but when we were trying to fit them on the device, we found that 500 megabytes is really not something that we can justify. So initially, because we also had to build a new inference engine from scratch, so we thought that maybe we should also change how we run those models and re-implement this. Why we had to re-implement the whole inference is because Java is it is a very portable language, but it's not a very portable language if you want to go embedded, because it has huge resource requirements. And embedded Java variants are not really equivalent with the cloud Java variants, so you get into all kinds of trouble. Finally, when you are running on Android, it's Java, but it's not really Java, and it gets very confusing very fast. So what our code is C++. So we built a new NLU engine in C++, and we built a new inference engine in C++, which handled those kinds of models that we trained in Mallet. And we didn't want to actually touch the training process. We didn't want to have a different models, because at this size, we thought that we could just have whatever the cloud has. It was good. So we are focusing on, when you are building models, you have data collection, training, then you have some post-processing and execution. So we are actually focusing on the last two stages. And so we were able to retain the training and the performance of the models while changing how we build them. So the first thing that we did was quantization. And quantization is pretty simple. It's, again, not very popular with those types of models, because in the cloud they are small and nobody thinks about optimizing them. But actually, when we started working on this, it turned out that it fits very, very well here. So typically with both max entropy and CRF, you are working with floats or double representations for your weights. And it's pretty large, so you get 8 or at least 4 bytes per parameter. And what we were experimenting with was clustering that into some K clusters. And if you do this, you essentially you can keep the rest of your inference process and just replace the weight of any member of the cluster with the centroid center or whatever some algorithm that you devise for representation of the cluster. And everything worked approximately the same. So in practical terms, the hyperparameters for testing that were K, so number of clusters that we had, and the algorithms for clusterization and computing those centers, those turned out to be simpler than we thought. So initially we were able to go down to K around 100 or something, but it turned out that when we get K to around 200, and 256 is a very good number, which is around 200, it turned out that we also can do linear quantization. So instead of having to hunt for very correctly aligned clusters. We could just quantize evenly with even gaps. And this solves a number of problems, but the chief problem that it solves is that now we have an 8-bit representation which aligns super nicely with computers. So this is where we went. So this alone means that instead of representing a single weight as 32 or 64 bits, you have 8 bits plus a lookup table which has 256 elements that maps back to those weights if you have a nonlinear centroid function at least. Okay, so that was solving one part of the model. So models in natural language processing are composed of two parts. So one is parameter weight, and the second is the feature dictionary. So the feature dictionary translates the features that you extract from the input into an index, essentially an index of the matrix or the array of those parameter indices. And Mallet, as most of the training software for those types of models, essentially packs those dictionaries into the model, and so the whole representation of the model contains all of the features as they are built during the training. And our models were pretty large on this in this regard, so we are using hundreds of thousands of features. As I mentioned, those are n-gram-based models, so essentially n-grams from the input compose into those features. They are pruned, but still after pruning, we are left with hundreds of thousands to millions of features. And this is pretty large. So what can we do with this? So perfect hashing. Perfect hashing is, again, very unappreciated technique for data storage. So if you want to keep your data in a very efficient mapping from some kind of data to sequential integers, perfect hashing is something ideal. In theory, what it means is we want to have a hashing function h which takes any input and hashes it uniquely so that for any input in the training set, they will all get different outputs. This is achieved by stacking multiple hash functions. And those hash functions are instances essentially of Marmor hash with different seeds. And the algorithm for that is, it fits on a single slide, right? So it's actually can be described even more shortly. So you take all the inputs, you try to hash them with one function. And if for a given output index you get unique mapping, then you keep that mapping as a 1, that's your hit. If there are conflicts, then you keep those conflicts into the next buffer, and then you repeat. So depending on the hashing function chosen, the hashing function has to conform to simple uniform hashing. So it has to have even probability distribution over the whole space, and you probably need to adjust your size of your array so that it doesn't cause any artifacts, but in general those are simple things. After you do this, you should get not very many conflicts in the first run, so in the next level you have only a fraction of your inputs, then you repeat the process, and you get a multi-level hashing which can get reconstructed pretty easily, because essentially when decoding you repeat the whole process. So you look at the table, if it's 1 then yes, you are done, if it's 0 then you have to go to the next table. Now that's just a set, right? So it only tells you whether something was in the input set or not. However, it's also possible to reconstruct the indices using ranking. And ranking essentially means that we are looking at the whole bit set that precedes the one that we have just found, and we are counting the ones before it. So it's amazingly simple, and you can accelerate it using succinct data structures. So instead of iterating over the whole bit set, we keep a lookup table which tells us that from start to index some chunk size, then count of bits is x, and then keep those those pre-index, pre-accumulated counts for all of the chunks that we have. and you take the closest chunk, and then you have to still count all of the bits remaining, but realistically, if you do this every, let's say, 128 bits, then you have up to 2 64-bit words to process, and this means 1 or 2 pop count instructions on any modern CPU, so it's essentially constant. Again, because it's just perfect hashing, and it's pretty unique, you get good results for the data that is inside the training set. You get possibly very bad results for the data that is outside of the training set. So you get conflict. And the way to avoid this conflict, there are numerous ways to avoid those conflicts. So you could completely separately from this process, you could use some sort of a Bloom filter, or what we are actually using is key fingerprinting. So for every match that we have, we keep an additional short bit vector, which is a constrained hash of this particular key. So what this helps is we don't have to worry about the whole keying space. We don't have to repeat the whole keying process as we would have to with a Bloom filter. We have now narrowed down to only potential conflicts with that particular key. So we know that we just have to do essentially take a hash and take as many bits as we want proportionally to the false positive ratio that we want to achieve. And that's it, right? So and that's just another hash invocation. So overall, initially we had strings, right? So the strings could be tens of bytes because those are n-grams. And after we threw out the strings, after we threw out the also the integers that they mapped to, because those was you have to keep both the string and the integer that it maps to, we are down to about 3.4 bits of data for the key and 1 divided by false positive ratio, logarithm of 1 divided by the false positive ratio of bits for the fingerprint table. So it's essentially around 8 bits or something, 10 bits per key. Now, how this performs in practice. So first of all, the model size. So this is what we are targeting towards to actually be able to reduce. So those models are split across multiple domains that we have and multiple ranking components. And there are different ratios, and I will explain this in a little bit, but if you look closely, we went from 150 megabytes total for domain classifications to about 12 megabytes. And the last line here is what you could do if you forgo the fingerprinting. So fingerprinting is actually the bigger component of the representation now. So if you didn't do fingerprinting, you could go down to 5 megabytes. So this is a 50-time reduction. For intent classification, you go from 200 megabytes to 8 megabytes, which is an even bigger reduction. And the difference here between the ratios, because those are both max entropy models, is actually in the training. So the training, our existing training for domain classification already replaced the features with 32-bit or 64-bit, depending on the model, hashes. So we didn't actually have the keys, the features. We just had hashes of them. So the reduction was smaller, but what it also allows us to do is to build better models, because we didn't have to do this hashing. So we initially did that kind of thing as a training level optimization even before we started this project. Now we didn't have to. So for named entity resolution, the reduction is slightly smaller, so it's about 10 times. And the reason here is that parameter weights are far bigger in numbers of parameters that we keep in CRF models is much bigger. We have to keep the transition tables, and this constitutes a far bigger portion of the model compared to the feature space, but still most of it has been essentially reduced down to almost nothing. So total size of the stuff that we are running actually on those devices is around 40 megabytes. And this was good. So how does it perform? And surprisingly good. So if you look at the aggregated results for overall data set, so if the compressed models perform approximately the same. So for the stuff that we had in our in-domain data set, our intent classification error rate and search error rate, it jumped, but it jumped by at most 0.86% for SER. And actually for things that we had out of domain, so the rejection rate performed better with the quantized model. So we got some benefits of, I didn't mention that before, but when we do quantization, because we do linear quantization, the weights that are close to zero get essentially flattened down to real zero. And this is actually a positive effect for those model types, and this is where it actually helps. So we achieved some improvement in error in out-of-domain rejection by using those models. If we look at this domain by domain, then we will see that this will depend. So there are domains that have bigger decrease. It's actually the models that we are mostly interested in is, I think, domain number 1, but that's less relevant. So it varies between 0 and 1.6%. Now, if we didn't do fingerprinting, which is essentially allowing our false positives to go wild, this jumps much bigger, so you achieve around 2% error rate increase, 3% on the intent classification. It still performs better on out-of-domain rejection, which is interesting. But overall, it's not as good as regular, as the bigger compression. And the size benefit, while going down twice, we had our other ideas for further reducing the size of our model. So currently, we're on top of that, we are doing some inline compression. And this brings it down to the sizes which are comparable to the models without fingerprinting. Okay, so that's the NLU part. So that's published in a paper. There was a reference to the paper in the slides. And on the ASR side, I wanted to kind of go back to our process. So ASR actually sits before NLU, and ASR already had a C++-based engine that we use in the cloud. It just used very, very big models. And the very, very big models were there mostly to handle music. So if you think about it, most of your vocabulary when interfacing with Alexa is music-related or shopping-related. So lots of words are only used for naming songs, artists, and things like that. And we didn't handle these cases. So the first and most obvious choice was trimming down the size of the model. However, we also did some experiments with model types. I'm going to go over that in the next slides. And we did all of those experiments on the final side of the model production. So we are training different kinds of models, and we're looking at how do they perform in embedded devices. We had a couple of those. Now, going to a bit of structure of the ASR model, it's composed of 2 layers. The first layer is acoustic model, and acoustic model is a DNN network which takes as its input features extracted from the audio signal, and its outputs are the distribution of probabilities over triphone hypothesis. So it will have, for English, it will have around 3,000 outputs, and each output corresponds to a single triphone. And from that, the second stage model, which is the language model, and typically is represented by an FST, Ngram-based FST, but potentially boosted by some rescoring algorithm. It's taking those hypotheses and generating potential words out of it. So this process the acoustic part is actually pretty similar on the cloud and on the embedded side. The language part mostly is happening in the second stage, and that's where most of the complexity is. And by simple reduction of the vocabulary, we were able to to make it work within reasonable bounds. However, the acoustic model itself didn't perform as well as we wanted, so it it used too much bandwidth. So what we did is we essentially had different ways of building those models. We looked at DNNs and LSTMs. LSTMs allowed us a simple CPU boost. However, because they were processed differently, the memory bandwidth went down, and efficiently they were not as good in the pure form. They had a big quality improvement. We tested DNNs and LSTMs, but did some parameter interpolation. So for LSTMs, this meant, well, later for LSTMs, this meant frame stacking. For DNNs, we were essentially running the DNN at every second frame and interpolating in the middle. This had a terrible quality loss. However, LSTM with frame stacking actually worked better than, so with frame stacking, we stack 3 frames and run the LSTM over those 3 frames again, rather than running on every single frame. This worked better. So this actually fit in the bandwidth for that we had, the memory bandwidth. So we are talking again about a device that has about 1 gigabyte per second of throughput, so which is very restricting here. So the second part was, again, we did some model quantization, and we went initially, we were using 16-bit models. We experimented with 8-bit models. Each reduction meant going down to with quality. However, we were reducing memory bandwidth significantly, and with 8-bit we finally were within real time, because we were fitting the model within the parameters for what we were able to transfer to the CPU. However, that was before frame stacking. From frame stacking actually cuts down the bandwidth 3 times, right? So that was the actual reduction that helped. And it's interesting to compare those optimizations to simply reducing parameter counts or hyperparameter tuning, because if we reduce the number of layers or just shrunk the number of parameters in each layer, the nodes in each layer, if we reduced 10% of parameters, we were seeing 1 to 2% word error rate increase. Now, doing quantization, we were seeing error rate increases below 1%, sometimes, and 16-bit didn't have any kind of increase. Similarly, for frame stacking in LSTMs, this was actually bringing better results. And the final thing that we did was rewriting the whole neural network execution. So the way that we multiply matrices in neural networks really matters when you are on an embedded device that has severe restrictions on how much data it can feed into the CPU and how much data the CPU can process. So typically when you need to be aware of how much data load pipelines there are, how much data processing pipelines are there in the CPU, and match those together. We were experimenting with, so essentially we have to go through one matrix and fetch its single rows from another matrix. You try to keep as much as you can in the cache. And initial implementation that we had and the existing implementation outside were pretty much fitted to a different device that we had. So it either overfed the CPU, which meant it ran over the cache, then it had to feed the cache back again, or it overfed the CPU, so it ran out of registers to actually perform the computations. We ended up with a pretty simple approach. So we minimized the amount of data processed, so it actually went single row at a time with multiple columns. And we fed as many data into the CPU as there were CMD registers. And this may sound complex. However, well, if you are working with quantized math, there aren't many very good implementations that you can choose from. And it's not as scary as you can think, so there are very good resources for doing assembly level optimizations. You have to write in C code, you don't have to write actually in assembly to do this, so that's something that I can wholly recommend. I think we're at the end of our time. Okay, so that's it. Does anybody have any questions?